Right, so we've still got a little bit of risk analysis left before we start looking at corrosion in subsea environments. So the one we're going to look at now is called Hazard and Operability Study, which is shortened Hazop. And it's a systematic analysis of how deviations from the conditions that we've set in our design or the operational procedures that are going to be performed, how these deviations can occur, and also how those deviations can cause risk. And all risk is, as it says there, undesired. We really don't want risk when we can avoid it. So the Hazop method, it stimulates both the designers, planners, operators themselves, the maintenance personnel, and everyone that's involved in either the design, the use of the design, or the operation that's going to be performed, to, in a systematic manner, to identify potential dangers and then process them to figure out ways that we can avoid these dangers. And it's a very flexible method, and it can be used in all types of industry. So this is not just something that is used in the oil and gas industry offshore. It is also used onshore, and it is used in whatever other industries you can think of, basically. Wherever there is real danger that can happen, where an undesired situation could cause either harm or maybe even death to people nearby. So a Hazop team will be set down, and it will be personnel involved in the system, the design of the system, or the procedure that is to be analyzed. And they perform this analysis. And it is important to know that the team of personnel will both include the people that are planning and designing and the people that are going to be using and performing the stuff, so that all of the chains and the link basically are together on this analysis. Because it might well be that if we're talking about a lifting operation and some lifting equipment that's going to be used offshore, it might well be that one of the guys working on the deck of the vessel will notice something with the design that, well, what if this happens? Then that part of the design will be a flaw that can potentially break, and that's going to be hazardous. And that might be something that the designers didn't think of when they were designing it. So it's very important to involve everyone in an analysis like this. And it starts off with a detailed walkthrough of the system or the procedure that you're going through. And then everything is broken down into smaller elements so that you can analyze each element. And these smaller elements are subjected to a systematic questioning in order to uncover if any deviation can occur. So basically you are subdividing your system into smaller parts, and then you're looking at each of these parts, and you are basically asking yourself questions. What if? What if this happens? How will that affect this part? What if this other thing happens? How will that affect this part? What if both of these two things happen together? How will that affect the part? So that is the main way of how this is working. And usually you define a set of keywords in order to base your questions on, such as not or none, more or less, before or after, part of or separated, or together or separated, opposite, other or different. So these are sort of keywords that you use to come up with questions. So you try to come up with questions with regards to more or less. What if we put more load on this lifting equipment? So putting less load on lifting equipment, that's not going to cause any unwanted risk. But if you put more load on it, you could overload it, and that's going to create risk. So that's one of the ways of using these keywords. So we'll do a small example. It's an analysis of a pipeline from one unit to another one in a processing facility. And the keywords that they are using in this Hazop is not none, such as no fluid flow through this pipeline. That's going to be a problem for the process. More, such as the fluid flow surpasses the design rate, or that we have a higher pressure than the design pressure. That can pose a serious problem to our design. And some of the causes and consequences that we uncover by questions like these can be completely unrealistic. So then you don't process them any further. So you just block them out then. If one of the questions that comes from the team is such a question that it's definitely not going to happen, then you just don't proceed further with that line of questioning. You just jump to the next question. And if some of the consequences that are uncovered by these questions are insignificant, we don't need to further process them either, such as using the more and less keywords on a lifting equipment. More load, that is very significant. We need to look more into more load, but less load, that's completely insignificant to risk with regards to risk in this. So the success criteria for use of this study is the correctness and the level of detail that we have in the drawings and the procedures, and also that we have sufficient background data for performing it. So basically, if you go into the processing plant in Kårstø and are supposed to do a Hazop study over there, and you have basically just hand-drawn sketches on a piece of paper, you're not going to be able to expect having a very high success rate on your Hazop study. But if you go in there and you have all of their technical drawings properly printed on paper, done by computer, and very detailed, then you have a much higher rate of success, or a much higher chance of getting much success with the study. Another thing that we need is the knowledge and the experience of all of the team members. So you can't put together a Hazop team that only consists of newly employed team members, because the newly employed team members most likely don't have any experience with the system or the design that you're going to do the study on, and they're not going to be able to draw on their experience of the system. Also, the ability of the team to use this method as a tool, both to promote their own imagination and also to visualize possibilities, and then in particular deviations and the causes of the deviations, and also the consequences of them. So it is really it is very similar to a creative process where you are just imagining that stuff can happen, and trying to look at how that is going to impact the system. We also need to have a team that is able to maintain a certain proportion to the severity of the identified risks. So, for an example, as I mentioned in the previous lecture, a meteor falling from the sky and slamming into whatever it is that we're designing, that's not a risk that we... it is a risk, of course, it could happen. There's a more than 0% chance that it could happen, but it's not very much more than 0. And the severity of this will, of course, the severity of the consequences will be very great, but there is nothing we can do to prevent it. So it is something that we need to just put behind us and quit focusing on. We need to focus on something else. So we're going to look at some examples of keywords and expressions that are in use. So the expression of purpose, and this describes how the item, the system, or the procedure is expected to work. So the purpose behind this is to perform some specific tasks. Deviation, Deviations are basically anything that deviates from the purpose, and we identify them by the systematic use of our keywords. Some Hazop teams use abnormality also instead of deviation. The cause, that is the reason for the deviation, and if the cause is realistic, it is going to be considered meaningful. So the meteorite falling from the sky, it's not a realistic cause because the percentage chance of it happening is so minimal, it won't be considered as a meaningful cause. The consequence, that is the result of this deviation, if it should occur, and if the consequence is insignificant, for an example, less load on the lifting equipment, it's not going to have any consequences at all because the lifting equipment is designed to handle even more load. So that's an insignificant consequence and we don't need to bother with it anymore. Risk, and that is the consequences that can cause harm to either the personnel that is operating it or the environment around it, or just material damage, so that you're going to damage some of the equipment nearby or something like that. So it's basically material values. It's going to cost money to repair it. So it's not going to send any people to the hospital or to an early grave or anything like that, and it's not going to make any impact on the environment, but you're still going to have to pay money to fix it. And the keywords that we're looking at, they need to be simple words that we use to analyze the purpose, and they can't just be any just words that you pick. They have to have some meaning to them, so they have to describe something happening, but they have to be simple also, so that it's easy to use them in the process. Yes? Yeah. I'll go back. Yeah, so the meteorite, it's not a realistic cause to be considering. So if it's not realistic, we won't put any meaning into it, because we all know in the back of our minds that a meteorite can fall from the sky, but it's not something that we go and worry about every day, and it's not something that we can worry about when we are designing something. So it's not going to be a meaningful deviation. Yeah. Was that a good enough answer? Yeah. So typical operations where we use Hazop studies is lifting operation. It's diving operations. It's also well operations, so anything that has to do with maintenance or installation on a well. We usually do a Hazop study beforehand, just to make sure that we've sort of thought about all of the causes and consequences beforehand. Drilling operations, marine operations, so anything that happens out at sea. And that's the typical operations for the offshore oil and gas industry. But of course, lifting is sort of universal. It also pertains to lifting operations onshore. If you're lifting something with a huge crane, big piece of concrete wall that you're going to lift onto a high-rise building, you still do a Hazop just to make sure that this is not going to be accidentally released from the crane hook and fall down and smash into the ground and possibly kill bypassers or anything like that. So you still do the Hazop studies. And just to show some additional keywords that could be used for specific operations, such as for a lifting operation, we might be using the keywords of loss of load. So basically that we are losing the grip on our load. It is unhooked from our crane hook or something like that. You might have a a jerking motion that happens, and if you then don't have any safety mechanisms on the crane hook, you could basically just have the load jump off of your hook. You could have a collision, so if the crane loses a little bit of its control over the lifted equipment, it could collide into something else. You could have a jamming incident where something jams. It might be the winch in the crane. It might be some of the sheaves that are guiding the lifting wire. It might be something else that jams so that it doesn't work properly. So what you do is looking at the causes, and the causes will create a deviation, and the deviation will lead to a consequence, but your keyword is meant to show you what the deviation could be. And by using a keyword to figure out what the deviation could be, you can easily, or not necessarily easily, but more easily, identify the cause and the consequences of that deviation. So by loss of load, that is going to be your deviation, basically, that you lose your load. The cause could very easily be that you don't have proper safety mechanisms on your crane hook. You're going to need some more better safety mechanisms on your crane hook that could make sure that you don't have any loss of load at all. The consequence could potentially be that it falls down and kills someone. So it's a very, very serious consequence to have. It could also be just that you lose it over the side of the, lose your load over the side of the vessel, and it's just going to sink all the way to the bottom. Not a serious consequence with regards to human life, but it will be very serious with regards to the economics of the parties involved. Both the company that owns the equipment that sinks to the bottom of the ocean floor, and also the company that's performing the lifting operations, because they're basically the ones that are going to be to blame. So that was it for the Hazop study. So then we'll start looking at materials and corrosion in subsea systems. And the main focus is corrosion when we're looking at materials, but we can also look at other significant factors, such as the yield strength of the material, the tensile strength of the material, the impact strength of the material, the fatigue characteristics, the manufacturing possibilities, the availability of the material, and also the economy of the material. All of this is going to impact our choice of material when we are working with subsea systems. But from here on and out, we'll be mainly looking at the corrosion factor, because you can avoid corrosion altogether almost by just making sure that you're using the best materials available, such as titanium and stuff like that, but that's going to make heavy impact on your economy, because titanium is very expensive. You will have good strengths, but the manufacturing possibilities are very poor for titanium. They require quite a lot of special care when you are manufacturing the titanium. So it's not only the material itself that is very expensive, it's also the manufacturing process, because they have to take so much extra care. We already know that seawater can be highly corrosive to many materials. That has to do with the fact that seawater has a pretty high content of salt in it, salts and minerals, and the combination of fresh water and minerals together is very electrically conductive, so that you get a fluid basically that's going to cover everything, and it's also going to be electrically conductive, so that you will have easy transfer of current between your different parts, since they are all in contact with seawater. But the well flow in a subsea system, it can also be highly corrosive to the materials. that are containing it. So we need to keep that in mind also. So corrosion, that is an attack basically on metallic materials, and that is through reaction with surrounding substances. So basically a chemical reaction. The metallic material is usually dissolved as the corrosion process continues. And this dissolving, it releases electrons, and those electrons are consumed where an opposite reaction occurs. So the release of electrons has an opposite reaction where they are being consumed, and this is where you are getting reduction of oxygen or development of hydrogen gas. So basically the anode-cathode process that you looked at in chemistry, where if you put an anode and a cathode into a liquid and you put some electric current going across them, you are going to have bubbles coming up from the cathode. The anode is going to be dissolved, and you are going to have bubbles forming with the cathode. And that's hydrogen gas or oxygen that's bubbling up. So the electrolyte, in this case either seawater or the well flow, it has to be electrically conductive and also a liquid. Then we have different kinds of reactions. If we have iron up top here, iron as an anode, that's going to release electrons. And the same with aluminium also, it's also going to release electrons. And then you have the cathode reactions, where you have the electrons that are combining with oxygen and water in order to creating different gases. And the anode reaction, it will occur in the less noble material, so a lower value on the galvanic series or the electrode potential series. So zinc and aluminium, they have a fairly close value to each other on the galvanic series. Zinc is a bit less than aluminium, and they are both much less than iron, and iron is also much less than copper. So if you put a piece of copper into a fluid, and then you put a piece of zinc into, and you put electric current onto this, the zinc is going to be dissolved, and the copper is going to be creating hydrogen gas, basically. Iron looks like it corrodes across the entire surface. We get this rusty brown color going across the entire surface. But if we look at the structure of iron, so back to the materials course that you had here, if we look at the structure, iron consists of confined crystal elements. And each of those elements has a different surface potential, which means that between each of those crystals there is a difference in the galvanic potential. It's a very small difference, but there is a difference there. So this means that we have each of the crystal elements inside the iron will have different galvanic series values, and we are going to have a reaction going on between them. So this happens all across the entire surface to all of the crystal elements there. And the crystal elements are small enough that we can't really see them without using a microscope, which means that to our naked eye it looks like the entire surface has rusted. But actually it is individual crystals that are being are rusting, basically. So the neighboring elements, they act as the cathodes and anodes for these. And iron oxide, which is what creates the rusty color, it is very poorly soluble in water, so it's going to stay on the surface as rust. But this also means that the more rust we get, the thicker of a coating of iron oxide we also get. So the more rust we have on top of the surface, the slower this process is going to go, because it has less contact, direct contact with the water. So that it isn't just because you have a rusty color on your steel or your iron, it doesn't necessarily mean that it is in danger of rusting all the way to bits and pieces. Once you have gotten this initial coating, the corrosion process slows down quite a bit. So it's still going on. So over time, it's going to cause a potential problem for your material. But it happens extremely quickly, this initial rust layer that makes everything look like it's corroded. But to get deeper in, it takes a little bit more time. So we have several different factors that influence the corrosion. So we have chemical factors over here, and we have physical factors over here. And now we are mostly looking at the well flow. So we're not looking at seawater itself, because in seawater itself, it is the fact that seawater is there that is the problem. But in the well flow, we have different compositions, so that's going to affect our materials. We also have different pressures and temperatures going on, so there's quite a lot that's affecting it. So let's look a little bit at the physical first. So with the physical factors, we have the total pressure in the system. That's going to have an effect on the corrosion process. We also have the temperature. The temperature can be fairly high when we have well flow coming directly from the reservoir, because usually the reservoirs are deep down and they are heated by the geothermal energy in the earth. We also have the flow rate. It's going to affect it. So if we have almost a standstill in our well flow, or if we have a moderate or a high flow rate in it. And the presence of solid particles, and especially the combination of a moderate or high flow rate and solid particles in it. So if you have some sand that's coming from the reservoir and coming with the well flow up, it's basically going to be sandblasting the inside of your system. And by doing this, it's damaging the surface of the material, and it's increasing the rate of corrosion. On the chemical side, we have a couple of other factors. So the amount of CO2 in the well flow, and the amount of H2S, so hydrogen sulfide. The presence of oxygen. So oxygen is the sort of big bad wolf when it comes to corrosion, because another word that you often use for corrosion is oxidization, and that means that we need oxygen in the loop in order for this to happen. Concentrations of chloride is also going to be a problem. And the pH level, so if it's acidic or if it's a base. In addition, we could also experience increased corrosion rate from the bacterial growth in it. So if you have bacteria that are growing inside the well flow, that could be detrimental to your corrosion resistance. So if we dissolve carbon dioxide in water, we get carbonic acid. So basically what you have in your soda, that's carbonic acid, CO2 dissolved in water. And that's also one of the reasons why it's not just the sugar in your soda that's bad for your teeth, it's also the fact that it's an acid. So it's harming your teeth that way also. And since it's an acid, it's also going to affect the pH level in your well flow. So it decreases the pH, and if we get a high partial pressure of carbon dioxide and a low temperature, that means that we can dissolve even more carbon dioxide into the water. So by cooling the water down and increasing the pressure, we can get more in. And that sometimes happens in a subsea system where you get cold temperatures, especially if you have pipelines going quite far along the seabed. So you get the approximately 4 degrees Celsius as the environmental temperature around it. So it's fairly cold, and then you also get a fairly high pressure. So that's going to create an even more acidic flow. And CO2 corrosion, it can be discovered in the form of deep pit corrosion, which basically means that it's creating very small but deep pits into the material, where it's just basically dissolving the material down in these pits, and also a general corrosion level, so just generally over the entire material. And pit corrosion can look something similar to this when you cut open the material and start examining it, where you basically can have these fairly large open pits, but you could also have some that are almost basically just look like a very small hole, but if you actually poke a needle into it or something, it's very deep, and you can see that it's very wide also, so it's going to be a lot larger. And you can have tendrils like this spreading out underneath the surface of the material. So that's having pitting corrosion happen in your material. That's very bad. So you really don't want that to happen, because you never know exactly how deep it's going to go. And since it goes deep into your material, it's also going to affect the strength of the material. For an example, the wall thickness of your pipeline can be affected by the pitting corrosion, and that's going to make that section of the pipeline handle less pressure. So we can add glycol or methanol into the flow. So by having injection valves in the Christmas tree, so we can add glycol or methanol there, and that's going to help us prevent the formation of hydrates in the well flow, and that's going to help us also keep the CO2 corrosion at a lower level. So by preventing the formation of hydrates, we also have a preventative effect on the corrosion. We can also inject inhibitors into it, especially where we are using carbon steel in the system. So we can use special inhibitors that we inject into the well flow, and that's going to have a positive effect on our carbon steel with regards to corrosion. But the inhibitors, they only prevent corrosion so long as they're in physical contact with the metallic surface. So that means that if you have a well flow where you're not utilizing the entire cross-section of the well, so the entire pipeline, the entire cross-section of the pipeline. So if you're not utilizing the entire cross-section, so you're not filling it up from bottom to top, you're basically just filling up parts of it, and it's just running along those lower parts. Your inhibitor will only be in contact with the lower parts of the pipeline. It's not going to be in contact with the upper parts, but the upper part might still be attacked by corrosion. So one way of doing this is sort of flushing your system, so that you are making sure that you're pushing through enough inhibitor fluid to cover the entire inside of the pipeline, and then you do this at regular intervals to try to refill sort of the coating that you're getting with the inhibitors. So hydrogen sulfide corrosion, also called sour service. That means that we have hydrogen sulfide dissolved in the water, and this is a weak acid, so it's slightly weaker than the carbonic acid, but it's still an acid, so that it's going to affect the pH value. And again, if we have a high partial pressure of CO2 combined with hydrogen sulfide, we are going to get an increased corrosion rate. So for the hydrogen sulfide, the temperature doesn't matter that much, but if we, in addition, have a lot of CO2 in there, it's going to affect it and increase it. So iron sulfides are formed. The iron sulfides formed are cathodic to the steel, so then we get corrosion. So the parts of the iron will react with the sulfide in the hydrogen sulfide, and they are going to create small crystals, and these crystals are acting as cathodes in relation to the steel in our material, which means that the steel is going to become the sacrificial anode, basically, so it's going to start corroding. And this also causes deep pit corrosion, or pitting. So we get the same illustration here for it. It can also lead to hydrogen-induced cracking. And this is pretty scary if you get in a situation where this can happen, because hydrogen atoms that are formed at the cathode reaction, they are absorbed into the metal material that we have. So the steel absorbs these hydrogen atoms into it. So basically the hydrogen atoms, which are the smallest atoms that we have, they sort of just basically run and hide inside the crystal structure of the metal. So they disappear into it, and they're going to stay just one and one hydrogen atom, so they're going to stay single atoms as they are diffusing through the material. But if they do find a structural defect, so somewhere in the crystal structure where there is a defect or maybe a very tiny crack or something like that, then these hydrogen atoms are going to gather there. And then we get hydrogen molecules instead of hydrogen atoms. And they will cause a very high hydrostatic pressure inside our material. And this can lead to local cracking of our material. And this happens without any external stress. So it's basically just going to crack. And no one knew that it was going to crack beforehand. So that's pretty, if this happens to some of your lifting equipment or something while you're doing lifting something very heavy and expensive subsea, and your lifting equipment suddenly has hydrogen-induced cracking in it, it could potentially lose enough strength that you are going to lose your load, and that can be very, very expensive. We can also have sulfide stress corrosion cracking, so SSCC, and this usually requires a smaller amount of hydrogen than hydrogen-induced cracking. But the hydrogen-induced cracking, it doesn't need any external stress in order to happen, while the sulfide stress corrosion cracking, it requires tension from an external source, and it also requires an active electrolyte in order to create cracks, basically. So if we look at both carbon dioxide, hydrogen sulfide, and chlorides combined, which sometimes happens in a well flow, you can have all three of these present, you will have your CO2 corrosion, which is not much affected by small amounts of hydrogen sulfide. And it can, in normal conditions, be calculated independently of the amount of chlorides that you have. So if you have a normal amount of chlorides in the water, it's not going to affect your CO2 calculations. Then you have the cracking, SSCC, where chlorides and CO2 are of great significance, so they're going to greatly impact the risk of having this cracking happen. And the temperature, yield strength, and the actual stress in the situation are also very significant for the sulfide cracking. And the effects of temperature is not properly understood yet with regards to the combined effects here. So we don't really know if it's better to have a low temperature or a high temperature or something in between. We don't know what's the best option here. What we do know is that 50 to 100 degrees Celsius seems to create a very large sensitivity to corrosion. And we can, if some of you are going to work with regards to corrosion in subsea stuff, you can take a look at the National Association of Corrosion Engineers webpage. They have, I think I put the link in here, so they actually have quite a lot of good courses that you can look at. I'm guessing that they're also very expensive courses, so preferably it would be your employer that pays for these courses, of course. So we have training and education over here. And then you have coating inspectors, cathodic protection program, general corrosion, general coating. You even have online courses that you can run, and pipeline industry courses. So they have quite a lot of relevant courses. So just the fact that we can do them online also helps. So I think we'll do a break before we start looking at the effects of seawater on corrosion. Right, so seawater and corrosion. So we can't really, although it would be nice in a perfect world that we demand that all of our materials used subsea are going to be corrosion resistant towards the seawater, that's not feasible. It's going to be way too expensive to do that. So this means that we only do this for details in our design. For an example, hydraulic or electrical couplings, the sealing surfaces in wellheads where you need to have a tight seal with regards to pressure, bolts, nuts, and movable mechanical components, because you really don't want something that's supposed to have movement. If this rusts a lot, it's going to basically, or for an example, if we have a shaft that's going through a hole, the iron oxide that will be created from the corrosion process, it's going to be on top of the surface mostly. So a thin coating of iron oxide, iron oxide, a thin coating of it won't be a very big problem. But if we get a much larger coating and we get it on both surfaces, we can start having a problem with the shaft that's supposed to be able to rotate in there. It basically gets locked in place by all of the corrosion, all of the rust that happens inside there. So whenever we have movable components, we prefer them to be corrosion resistant to seawater. So AISI 316L, it has a very good corrosion resistance to seawater. That's one steel type that we use. And when we're looking at seawater corrosion, we are especially looking at different materials that will be corroding each other. So for an example, if we have aluminium and steel combined together in one design so that they are in contact with each other electrically and also in contact with seawater, both of them, then what's going to happen is that the aluminium is going to become the sacrificial anode and the steel is going to become the cathode. So basically we're going to start dissolving the aluminium. So the seawater will start eating away from the aluminium. And this is what we call galvanic corrosion. So seawater and two different kinds of metal are in contact with each other. So these three components, all of them in contact. And the aluminium, which is the less noble material, will become the sacrificial anode. So one way around this would be to add a third metal in here. So if we had strapped on a zinc anode here as well, the aluminium might be saved, but the zinc and aluminium are fairly close to each other, so it might not be saved by it, but it should be a little bit safer at least. So we're going to look a little bit at different kinds of materials that we can use. So we have carbon steel, and it has an increased sensitivity to the sulfide cracking with increased strength. So the stronger carbon steel that we use, the higher the sensitivity is going to be with regards to hydrogen sulfide and cracking. So the time until fracture is decreased with an increased amount of hydrogen absorbed. So the more hydrogen it gets to absorb, then the less time we have before it's going to crack. We have ferritic and martensitic steel, which is what we usually call stainless steel. The reason why it's called stainless steel is that in normal conditions, you won't get that surface coating of rust on it, so it won't turn that rusty brown color. And it is practically immune to CO2 corrosion up to 150 degrees Celsius. And chloride and hydrogen sulfide limits its use. So it's going to react to chloride and hydrogen sulfide. So in environments where we have a lot of that, we need to make sure that we limit the use of the stainless steel. We have austenitic steel and nickel alloys, and the AISI 316L is one of these, and it is limited to up to 60 degrees Celsius due to risk of stress corrosion in chloride conditions. And in a chloride condition, it basically means that we have to make sure that the temperature is less than 60 degrees Celsius. So if we are in a chloride condition, for example, in the well flow, we have chlorides present, we need to make sure that our well flow keeps the temperature lower than 60 degrees Celsius if we are going to use the 316L. Yeah?
If they are going to determine what material they will use
Yeah.
in respect to the well, how do they know the composition of the well?
It's when they do the test drilling to figure out the reservoir and what's in the reservoir. So when they do the exploration drillings and all of this, they're going to do samples from the well, just to make sure that they know what's going to come up from the well, the reservoir. But apart from that, they can do miscalculations and end up with a different well flow from what they had anticipated from that reservoir. So it does happen that they do miscalculations with regards to the material. And then one way of trying to sort of fix that will be to use inhibitors and try to inject stuff into the well flow in order to counter the corrosion effects. So with duplex steel, ferritic austenitic steel, it has a very high strength and a relatively good corrosion property. And there are no serious operational problems that have been reported with duplex steel. But there are some manufacturing problems that have been reported with it. So you can't just assume that designating duplex steel as the material for your design is going to work out, because it might actually be that they're going to have quite a lot of problems manufacturing your parts in duplex steel. So they're a bit limited with regards to manufacturing possibilities when it comes to duplex steel. Not exactly like with the titanium. Titanium is a little bit different when it comes to manufacturing, because with titanium, it requires you to use a separate set of equipment when you are manufacturing it, which basically means that you have to have a completely separate workshop where you have all of the manufacturing equipment in there, all of the CNC machines and everything, and they only manufacture titanium parts. So you can't do anything else with those machines, because as soon as you put a different material in there, you're basically contaminating the equipment, and that's going to be problematic with regards to your titanium, because then you risk your titanium actually starting to corrode, so it's going to lose its corrosion resistance. With the duplex steel, it's a little bit different, because there it's certain of the manufacturing processes that are difficult to do. So there are some of the parts there that they can have some trouble with achieving. And one of those are specific welding types and how to do that. Aluminium is another material, and it has low weight. But we have to choose a seawater-resistant alloy of aluminium. Aluminium, whenever we say that we're using aluminium, we're using an aluminium alloy. If we use straight-out aluminium, it's very soft and malleable, so it really doesn't have that much strength. But as soon as you start mixing in other materials into it, you're going to get alloys that can be quite high in strength. But we have to keep the galvanic corrosion in mind when it comes to the aluminium with regards to its low value on the galvanic series. Titanium, it has a very unique combination: high strength, low weight, and extremely good corrosion resistance, and it can also tolerate very high temperatures. That being said, for an example, the nuclear submarines of the Soviet Union, or now Russia, they usually have their entire hulls made out of titanium. So basically the entire submarine, everything that is in contact with seawater in the submarine is made out of titanium. And these nuclear ones, they are really huge. They're not the small diesel engine type stuff. They're basically monsters compared to other submarines. So using titanium there, that I can't even imagine how expensive that must have been when they were creating those. But the upside to it is that many of these were created in the 70s, 80s, and they're still running. So they don't really have corrosion problems or anything like that, because the entire outer shell is titanium. But we have a high cost, and the manufacturing and welding processes become basically extra additions to the cost with regards to having to use specialized equipment for it. Not that the equipment is specialized in the regards of being different from regular manufacturing equipment. It's just that you have to have them reserved for only titanium when you're working with it. We also have polymer materials and composite materials. So basically different kinds of plastics that we can use, and combinations of plastic types and fibers. And they are highly corrosion resistant. They won't really corrode when you put them in the seawater or anything like that. It's very low weight. And then they can have a very wide range of properties. Of course, you won't get any plastics that will have the same kinds of strength as your different kinds of metals. So whenever you need something with high strength, you usually have to go for a metal. But if your part really doesn't need to have that much strength, it might be possible to go for a polymer material instead. And that's going to save you quite a lot of grief with regards to the corrosion properties. But there is one thing that we need to keep in mind with polymer materials, and that is that they can absorb water. And if they absorb water, they usually also swell, so they're going to increase the volume when they absorb the water. So that means that if you have a block of a specific kind of polymer that might be 1 meter by 1 meter and 10 centimeters thick for use somewhere in your equipment, once you get it down to a certain depth, it's going to absorb a certain amount of water because of the hydrostatic pressure, and it's also going to swell, so it might suddenly be quite a few millimeters, maybe even centimeters thicker in all directions. So that can cause quite a lot of problems with regards to having it fit inside other components, for example. So it's something we have to keep in mind. Usually, if you're using a polymer material, the absorption rate and a percentage of swelling is going to be mentioned in the data sheet, where they actually run tests on it down to different depths, just to check how much it's going to absorb and how much it's going to swell, so that you could take it into account when you're doing your design. So basically just make room for swelling. There we have one of the tables that are given in the compendium, which gives a lot of properties up here with regards to strength, brittleness, corrosions, different types of corrosions and temperatures. And then the materials down here. We also have cost set up as one of the properties here. And then they've been given grades from 1 to 5, where 1 is the most favorable and 5 is the least favorable that we want. And we can see with regards to cost, carbon steel is very favorable. We move down to titanium, that's the least favorable. And also some of the polymers and composites can be very expensive. So they can be anything from cheap to very expensive. So basically we can look at different kinds. So if we need something strong, we're not particularly concerned with cost, because it's strength that is really important to us. And we also know that we're going to have CO2 and H2S corrosion. Then we can look at strength. So we want something with a high strength, titanium for an example. And it is also very favorable with regards to CO2 and H2S corrosion. But it is very expensive. So if we go down to polymers, very unfavorable with regards to strength. It's not really all that strong, but it's very favorable with regards to the corrosion. We could look at martensitic steel, very strong and also very favorable, and quite a lot cheaper than titanium. So it's sort of a way of doing a guesstimate of what kind of material would be useful to have in your particular situation. So this was the last one from that one, and then we have also the Appendix A that I've put in here. The rest of the appendixes, I think there's B and C, maybe D also, I can't quite remember. But those are very short, basically just one page. One of them is even just a table of contents from one of the NORSOC standards. So I won't really bother with putting it up here. But for Appendix A, we're basically going a little bit back to internal control systems that we had with regards to rules and regulation. So we'll look at different tasks for internal control systems. So the licensee, with regards to having the license for developing a particular reservoir or area with reservoirs, is supposed to have internal controls, and they shall, amongst other things, secure that we, with regards to organization, have responsibility, authority, and communication lines clearly defined and understood. So that it's going to be very easy to understand who is responsible for what, who has the authority to make which decisions, and who do we need to contact in particular situations. With regards to training, it's supposed to ensure that we have competent personnel utilized during both planning and execution of every phase, including construction, fabrication, installation, and operation. So basically all the way from just planning the development and all the way to operating the finished field. It's also supposed to make sure that the employees and entrepreneur personnel get all of the training that they need in order to perform their work tasks. With regards to documentation, it's supposed to make sure that we have administrative systems for document control in all phases of planning and execution, of exploration, drilling, extraction, and production. So basically even before you start developing a field, when you're just looking for a field to develop, even then you're supposed to have all of this in place. And it's supposed to ensure that information and documentation is submitted to the government in accordance with rules and regulations and guidelines, and within the deadlines that are being set. So with regards to quality, It's supposed to ensure that purchasing documents, specifications, and anything that has to do with stuff like that maintain the sufficient requirements for quality control, so that the documents that you get when you are buying equipment from external suppliers, that everything has all of the paperwork that it needs. That's very important with regards to being able to document that you basically have what you need to do a job. It's supposed to make sure that entrepreneurial quality control is assessed and taken position on and subjected to system revisions. And the specified quality of deliveries shall be documented through test reports and certificates and whatever else ways that you can document it. And that you have a quality management system, including quality control during operation, and that it is functioning efficiently. And that corrective measures are put in place when quality control uncovers discrepancies from the established specifications. So basically, it's not just enough to have a quality control system, you also have to make sure that you do things to fix, and that you do stuff to make sure that whatever you uncover in your quality control system gets fixed. With regards to execution, we are supposed to have satisfactory operational procedures with regards to, for example, diving, drilling, startup, production, inspection, testing, and maintenance. We need to establish these procedures and we need to follow them. We need to have functional ability of operational procedures, and they are to be verified by the internal control system. And specifications for repairs are to be established, and the specifications are to give sufficient basis for and set sufficient requirements of the execution of the repairs, just to make sure that we have the proper amount of quality in the work that is being done. Temporary equipment can be installed and used in a responsible manner and in accordance with the established specification according to the quality control, internal control systems. And we're also going to ensure that the modifications will not be detrimental to the original safety specification, so that if we do install temporary equipment or if we do modify some of the equipment we have, it's not going to affect the original specifications. And the procedures are supposed to be shaped in such a manner that safety requirements are maintained even if the facility or the device is used in an alternative manner. Safety-wise, we are to perform safety assessments before startup of exploration drilling, before final choice of development solution, and in the following phases, including operation. And the safety assessments are in all phases to also cover pollution to the external environment. The individual administrative decisions made by supervisory authority are to be made known to the employee elected representatives and any entrepreneurs that are also affected. Basically, the internal control system has to make sure that if the supervisory authority comes into the company and says that you need to change this, the company has to make sure that the union representatives and the entrepreneurs get to know what needs to be done and fixed. So the company management can't just try to hide it away. Licensee employees and entrepreneur personnel are to be familiarized with possible accident, health, and pollution risks, and that they are given the necessary information, training, and drills. So with regards to drills, it's sort of like the evacuation drills that they'll have on a rig, for an example, but also training on land. And workplace safety shall be maintained during labor disputes and abnormal operational conditions. So a labor dispute, so if the union wants a higher pay, wants a pay rise for all of their members, the company refuses to do that, we have a strike on our hands, then still the internal control system is supposed to ensure that we maintain safety, so that even though some of the employees are on strike, the safety is still maintained. Standby readiness. The standby readiness system is to be established and maintained in such a manner that necessary measures can be executed effectively and affected authorities notified. So in accidents or dangerous situations. So that's with regards to if there is an accidental spill in an oil rig or from a tanker or anything like that, you have oil in the water. They are supposed to have standby systems ready so that they can try to start up the cleanup process as soon as possible, that they don't have to wait for equipment to be ferried in from somewhere else. In the meantime, the oil spill might have a chance to drift off somewhere else and spread out onto a larger area. So that's one of the reasons for having the standby readiness. Safety and health personnel are to be able to perform their tasks after the current rules and regulations. So just making sure that they have the equipment that they need and the necessary training. For the work environment, that within the jurisdiction of the work environment law, a continual control and mapping of the work environment in the workplace is to be performed. And this is with regards to risky conditions, health risks, welfare conditions, and necessary corrective measures are to be executed. For an example, with regards to health risks, if there is an area in the workplace with a lot of noise, one of the necessary corrective measures might either be to put up some noise insulation, or if that is impossible, maybe make sure that you have protective gear available close by, so that anyone walking into that area can just pick up some protective gear and put it on. Experiences from organized safety service and company health service are important to the internal control systems, and they are assessed and taken into account. So for an example, the safety representative, if they have an inspection and find something, it has to be taken into account. And plans of significant impact to the work environment, a large modification of a rig, purchase of machinery and equipment, streamlining work processes, everything is to be assessed in the organized safety service, just to make sure that it won't have a negative impact. With regards to pollution, we need internal control to have continual control and mapping of pollution risks to the external environment, and the personnel needs to be at all times able to execute their tasks so that damages or disadvantages to the external environment from pollution are avoided or minimized. So that was everything. We've gone through the entire appendix there. It's basically just a list of stuff that an internal control, and this was tasks amongst others. So this wasn't a complete list even. So internal control systems, they're very important when we're working, especially in a workplace like an offshore environment. So that was everything. We've gone through the entire compendium, basically. I think we'll stop for now for the final time. As I mentioned before the weekend, I have my own exam that I'm going to be working on starting from tomorrow morning. But December the 2nd, I'll be back in the office, and if you have questions with regards to the exam and stuff, you can reach me there. Before that time, you can reach me by mail if it's important. So, good luck with your exams. You'll have a couple before I'm back, I think. So, very good luck with that.